the law talks about two types of changes: physical and chemical. Let's look at an experiment to verify the part about the physical changes. Let's place some ice cubes in a dish and weigh it. Let's say that the weight is X. If we heat the ice, it will melt and form water. If we weigh the water, we notice that the weight is the same as the weight of ice. This proves that when matter undergoes a physical change, like in this case, the total mass of the reactants is equal to the total mass of the products. Now, let's verify the part about chemical changes.
We'll fill sodium chloride and silver nitride in the two limbs of Landau's tube.
Now, let's seal both the limbs with a rubber cork.
Let's weigh the tube and note the weight. This is the weight of reactants before taking chemical reaction. Now, tilt the tube to mix the solutions thoroughly. Reaction takes place, and we notice that a white precipitate of silver chloride is formed in the tube along with sodium nitrate solution.
Let's weight the tube after the reaction. We observe that the weight remains the same. Thus, we can conclude that when matter undergoes a chemical reaction, the total mass of the reactants is equal to the total mass of the products.
That is, during any chemical reaction, matter is neither gained nor lost.
Hence, this law is also called the law of indestructibility of matter. Now let's look at the next law. Law of definite proportions. As the name suggests, this law deals with the composition of various elements present in a compound. In 1799, Joseph Proust proposed the law of definite proportions. This law states that a pure chemical compound always contains the same elements combined together in the same fixed ratio by mass. For example, the water we get from any source such as river, well, lake, sea, or from any other place always contains hydrogen and oxygen elements in the ratio of 1:8 by mass. Thus, we can say that a given compound always contains exactly the same elements in the same fixed proportion by mass. However, this law does not apply if an element exists in different isotopes, which may form a compound.
For example, if a carbon-12 isotope combines with oxygen to form carbon dioxide, the ratio of carbon to oxygen is 3:8. But if a carbon-14 isotope combines with oxygen, then the ratio of carbon to oxygen is 7:16. Another limitation of the law is that elements may combine in the same ratio, but the compounds formed may be different. For example, the compounds ethanol and dimethyl ether have the same number of carbon, hydrogen, and oxygen atoms, but their arrangement is different. That is, the compounds are different.
In 1804, Dalton proposed the law of multiple proportions. This law states that when two elements combine to form more than one chemical compound, then the masses of one of the elements that combine with the fixed mass of the other element bears a simple ratio. For example, when the elements carbon and oxygen combine, two compounds, namely carbon dioxide and carbon monoxide, can be formed.
As seen in the equation for carbon dioxide, 24 parts by mass of carbon combine with 32 parts by mass of oxygen.
Whereas, when carbon monoxide is formed, 12 parts by mass of carbon combine with 16 parts by mass of oxygen.
These masses of oxygen bear a simple ratio of 32:16 or 2:1. In these reactions, a fixed amount of carbon is combining with multiple proportions of oxygen to form carbon dioxide and carbon monoxide.
Similarly, when sulfur dioxide and sulfur trioxide are formed, the masses of oxygen bear a simple ratio of 32:48 or 2:3. In these reactions, a fixed amount of sulfur is combining with multiple proportions of oxygen to form sulfur dioxide and sulfur trioxide. In 1808, Gay-Lussac put forward a generalization which defines the relationship between volumes of gaseous reactants and products. This generalization is known as Gay-Lussac's law of combining volumes. It states that when gases combine or are produced under similar conditions of temperature and pressure, volumes of reacting gases as well as the products bear a simple ratio to one another.
For example, when one volume of hydrogen reacts with one volume of chlorine, the result is always 2 volumes of hydrogen chloride. Thus, ratio of volumes of reactants and products of this reaction is simple.
Another example is when 1 liter of nitrogen gas reacts with 3 liters of hydrogen gas to produce 2 liters of ammonia gas. Since all the reactants and products are gases, the mole ratio of nitrogen gas to hydrogen gas to ammonia gas is same as the ratio of the volume of each gas participating in the reaction. That is, 1:3:2. In 1811, Avogadros suggested that matter consists of 2 kinds of particles, namely atoms and molecules. He defined an atom as the smallest particle of an element, which can take part in a chemical reaction, and may or may not be capable of independent existence. A molecule is the smallest part of an element or compound which is capable of independent existence. He concluded that since the smallest particle of a gas, which can exist independently, is a molecule and not an atom, hence, the volume of gas must be related to the number of molecules. he proposed a law known as Avogadros' law, which states that under similar conditions of temperature and pressure, equal volume of all gases contains equal number of molecules. For example, 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride gas. For this to be true, it would mean that the number of molecules in 1 volume of hydrogen, N, will be equal to the number of molecules in 1 volume of chlorine, N. During the reaction, they will form 2 volumes of hydrogen chloride gas, which will contain N plus N, that is, 2N number of molecules, which means that the number of molecules in 1 volume of hydrogen chloride is equal to N. Thus, proving Avogadros' law. While scientists studied matter and formed the laws of chemical combination, they were unable to answer some questions. For example, why are 2 elements different, or why do elements combine to form compounds? Dalton studied the structure of matter, and in 1808 he proposed a theory to describe the structure of matter. This theory was named after him as Dalton's atomic theory. The theory states that matter consists of extremely small, indivisible and indestructible particles called atoms. Atoms of the same element are identical in shape, size, and mass. Atoms of different elements have different sizes, masses, and chemical properties. Atoms of 2 or more elements combine in a fixed ratio to form a compound. Atoms can neither be created nor be destroyed during a chemical reaction. Chemical reactions involve combination, separation, or rearrangement of atoms. Scientists used Dalton's atomic theory for a century. However, in the beginning of the 20th century, scientists like Sir J.J. Thomson, Lord Rutherford, and Niels Bohr came up with new findings, which revealed some drawbacks in Dalton's atomic theory. The drawbacks of Dalton's atomic theory are: it could explain the laws of chemical combination only by mass, but not by gaseous volumes. It could not explain why atoms of different elements have different masses and sizes. It could not explain how and why atoms of the different elements combine to form compounds. It failed to explain the nature of binding forces between the atoms and molecules, which accounts for the existence of the 3 states of matter: solid, liquid, and gaseous. And it makes no distinction between the ultimate particles of an element or a compound. So, they modified Dalton's atomic theory, and it is now known as the modern atomic theory. Here are the key findings of the theory. An atom is no longer considered indivisible. This means that an atom is a complex structure and is made up of electrons, protons, and neutrons. Atoms of the same element may have different atomic masses. Such atoms are known as isotopes. For example, a chlorine atom may have an atomic mass of 35 and 37. Atoms of different elements may have same atomic masses. Such atoms are known as isobars. For example, a calcium atom and an argon atom have the same atomic mass, that is, 40. From this, we can also conclude that atoms of different elements may be identical in one or more aspects. The ratio in which different atoms of different elements combine may be fixed and integral, but may not always be simple. For example, the elements C, H and O combine to form sugarcane. The ratio of the elements 12:22:11 is fixed and integral, but it's not a simple ratio. The atom is the smallest particle that takes part in a chemical reaction. In nuclear reactions, atoms of an element can be changed into another. For example, atoms of nitrogen can be changed to oxygen through bombardment of alpha rays.